All right, so let's start with the homework. If you have any questions, let me know.
I have a question.
Sure.
So on problem one, we're supposed to approximate the forward and backwards error using the approximation that you gave us there. So are we supposed to have y plus delta y is equal to y plus delta x over x and using that to solve for the forward and backwards error?
Let me see. Let me go look for it. So, all right. So what was your question again? And try to share it.
Yeah, so my question is, are we just setting the far left?
Or you muted yourself.
Sorry. Are we just supposed to be setting the far left and the far right equal to each other and using that to solve for the forward and backwards error?
Yeah, so the forward error is the easier one, right? You just and it's always relative, right? So you need to divide by y basically.
Yeah.
Mm-hmm.
Well, I just got a little bit confused because when I did that, are we supposed to be using, so setting y plus delta y is equal to y plus delta x over x, the extreme left and right of that equation, and using that same equation to solve for both the forward and the backwards error, but then the condition number, it just seems like everything cancels out and it seems kind of a circular argument almost to me.
No, you should get some. You should get something.
When I do it like that, the condition number is absolute value of 1 over ln x.
Right.
And is that correct?
Yeah.
Oh, okay. Then I guess I just kind of confused myself with everything.
Yeah. So it becomes problematic at 1, right?
Mm-hmm.
Because it vanishes.
Okay. Then that answers my question. Thank you.
Other questions? Did you find 1, 2, and 3 challenging? The book calls them easy. The first time I looked at a 1, I didn't find it easy. But then, yeah, there is an easy way of doing it. But it's a little.
I thought the first question in 1 was easy, but the second wasn't as easy. And I was expecting it to be kind of a correlation and be even easier, but it wasn't. And then I found the third one to be at least straightforward.
Yeah.
And the second one took the most thought for me.
Yeah, they were all not too difficult. I think the hardest part is putting them into LaTeX because I'm still figuring out how to use LaTeX.
That's good. If you, if you run up against the deadline and you want to handwrite them and take a picture, that's fine too. If you do it in LaTeX, you do me a favor because LaTeX is very legible. But if you are hard pressed, don't worry about it.
Okay.
All right. right. Any more discussion of the homework? All right, so I guess we can start with today's lecture. And before we continue, I wanted to kind of put down some milestones, some bases that we all can agree with, and then go from there into more elaborate things. But so I wanted to do a little review of matrix theory. And I don't know how fresh in your minds this is, but it also kind of varies. Sometimes you take a matrix theory course and it doesn't really cover everything that ideally should be covered. All right, so let's assume that I have a matrix. It's an n by n matrix, so I'm going to write it like that. It's a square matrix. And then we can talk about an eigenpair, right? So then U lambda is an eigenpair and I will end up abbreviating this just E pair. Eigen is a German word, and it's kind of annoying to write that all the time. But so U and lambda is an eigenpair for A if what? What is the condition? Remember?
Then the matrix multiplied by a vector is equal to the same vector multiplied by lambda. So AU equal to lambda U.
U. That's true. There's another condition. U should be non-zero. So U should be a vector, but not the zero vector. And lambda should be any real. And then they should satisfy this eigenpair equation. We say that U is an eigenvector for A, and lambda is an eigenvalue. When this happens, right? But it's really a pair. It's a pair. They come together, and I'm gonna need to add some space. Right. So let's recall that basically you can move the right-hand side to the left-hand side and write it like this. And then if you use the identity matrix, lambda times the identity matrix times U, right? And factor, then you can also write it like this. So in other words, the eigenvector U has to be non-zero, right? We already know this. And also has to be in the kernel of this matrix A minus lambda I. There are different ways the kernel or the null space, those are equivalent words for the subspace of all the vectors that make a matrix vanish, right, when you multiply. And this, the set of all these things, is called the eigenspace. So far, so good?
Mhm.
All right. So, all right, so if you remember, just because U is an eigenvalue, it doesn't mean that it's the only thing in the eigenspace, right? So the eigenspace can be quite large, and you can compute the dimension of it. So the number, the biggest number of linearly independent eigenvectors that for the same eigenvalue, that dimension is called, you remember what this is called?
A nullity.
The what?
A nullity.
It's the nullity, but for the eigenvalue, it's called the geometric multiplicity, right?
Ah, yes, yes.
All right, so that's the geometric multiplicity of lambda, the dimension of the eigenspace. Now, the other thing you can do, if you just want to know whether whether lambda is an eigenvalue, is you can take the determinant of lambda I minus A, right? And if the determinant is non-zero, then this is non-singular, so it's invertible. And there's only going to be one solution to this equation over here. Right? If this is invertible, then the only solution is the zero solution. And so if the only solution is the zero solution, then there are no eigenvectors because the eigenvector have to be non-zero from up here. So in order for lambda to be an eigenvalue, the determinant of this matrix needs to be zero, because then the matrix is singular, and then there will be infinitely many solutions because it's a homogeneous system. Right? So the other way you can check if lambda is an eigenvalue is by taking this determinant, and this actually has a name. It's called, turns out, if you just write it down, it's a polynomial, and it's called a characteristic polynomial. Right? So you write it down as a polynomial in lambda, you factor it, you find the roots, and those are your candidate eigenvalues. And in fact, from general theory of polynomials, we know that there are always exactly n complex roots, right? And that's kind of a problem because, you know, our matrix A is real. And so if we get a complex root, it's not clear what we're going to do with it. But in any case, assuming that, you know, we don't worry about that for a moment, you can always factor your polynomial into a product of these monomials. And there could be some, you know, repeated monomials. So I don't know, some powers up here, right? This is the general factorization of a polynomial. Now you might wonder about the leading term, but actually because of the way I've written it down, the leading term is going to be lambda to the n. So it's really going to look like this. And these exponents, alpha j, are called the algebraic multiplicity of the corresponding eigenvalue. And it's a fact that I'm not going to try to prove at this stage, that the geometric multiplicity is always smaller than the algebraic. All right. So it's just a fact of life. When you add up these exponents alpha, you're going to get n. So you don't miss anything, but in the geometric one, you could actually be defective, right? All right. This sounds okay so far.
Yes.
All right. So next, what you say that A is diagonalizable mouthful if you can find a basis early B consisting of n vectors u1 through un or Rn, such that the UJs are eigenvectors. All right. And so in this case, clearly the geometric multiplicities will add up to n as well. So it's a situation where there's no defects. And what do we mean by a basis in this case? Since we have n vectors, the only thing needed to check that this is a basis is to check that they are linearly independent, right? And then once they're linearly independent, if you have a vector x, you're going to be able to write it out as a linear combination of the UJs with some coefficients AJ. And then if you want to know what happens to X, when you apply A, you can use the linearity and pass A through the sum and take out the coefficients even, like that. And then because the UJs are eigenvectors, you get this, right? And so you go from a vector that has these coordinates in the UJ basis to a vector that has these coordinates in the UJ basis. And that's, you can represent that as a matrix, as a diagonal matrix, lambda, by putting the lambda j's on the diagonal, right? So one. So that's why we call it diagonalizable, because up to changing the basis, the matrix A becomes diagonal. And in fact, we can even be more precise here. These set of coordinates AJs are uniquely determine X because of the linear independence. So we could form a matrix S using the basis vectors, and then notice that X, right, if you remember how matrix multiplication works, when you multiply U1, UN by A1, AN, you get the linear combination of the columns. Right? In other words, X is S times the coordinates of X in the basis B. And because of, you know, we have a basis, S is invertible. And so we can rewrite, you know, what we did up here by saying that we can rewrite what we just said up there by saying that AX in the coordinates of AX in the B basis, right? These are the new coordinates here, AJ lambda J. They're going to look like this. Lambda 1, A1, lambda N, AN. Right? And from the point of view of these numbers, it's what happens when you take the matrix lambda and you apply it to A1, AN. So it's lambda times the coordinates of X in the B basis. And then if you use this property here, on both sides, you get that if I multiply by S, and use the invertibility to invert here, let's see, what did I want to do? Oh yeah, so this here is going to be AX, and this is going to be S lambda S inverse X. And so another way to say that by changing variables, A becomes diagonal, is to say that we can factorize A as an invertible matrix, as a diagonal matrix, and then the inverse of that same invertible matrix. So this is a matrix factorization, which is called a diagonalization. But at least for me, when I see these type of matrix factorizations, I always have to think about what are they telling me, right? And this fact that if you change coordinates, the matrix becomes diagonal. This makes more sense to me, kind of in a hands-on type of way. I don't know. This is very compact, very nice, very useful, even in computations. But it can hide a little bit of the mechanics that are going on in the background. I don't know what you think, but any comments? Sorry, I couldn't hear anyone, but that made sense, right? All right. So this is all fine, but actually, the more important thing, I think one of the most important theorem that should be covered in a matrix theory class, at least in my opinion, is the spectral theorem. Right? This is probably the most impactful theorem in that course. So if you have A, n by n, you have a square matrix, which is real, and A is symmetric, meaning, if you remember, that it's equal to its transpose. This is my notation for n. Then what happens? Do you remember? What's special about symmetric matrices? Right? Are they, yeah, somebody's talking. Anyone? Are they diagonalizable? So this is the most important fact, right? Symmetric matrices are always diagonalizable. But even more than that, spectral theorem says that not only there is a basis of eigenvector, then there is a basis, again, U1, UN, or Rn, of eigenvectors, but so it's diagonalizable. But moreover, this basis has extra properties, right? So that B is orthonormal. So it's an orthonormal basis, right? I often gonna write ONB, orthonormal. Or Rn. That's special, right? So that's very, very useful. What does it mean to be orthonormal? It means that when you take the dot product of a vector ui and a vector uj, well, you're going to get 0 if these two vectors are different, and you get 1 if they are the same vector. So in other words, these are vectors of norm 1, right? Of Euclidean norm 1, and they are all mutually orthogonal. Does this ring a bell at all?
Mm-hmm. Leading to the very misnamed categorization of a matrix when we call the matrix orthogonal, but we really mean that its collection of vectors are orthogonal and normalized.
True. Yes.
That one confused me for a while. I was not happy with the inconsistency of the naming.
Yeah, you're right. You're right. Maybe unitary is an equivalent term that's a little bit better. But yeah, you're right. So, right. So if we put these into a matrix U, then not only this is going to be invertible, but the inverse is going to equal the transpose. So that's going to be an orthogonal matrix. All right. And so the same change of variable, so you want to imagine this, this is the unit sphere in Rn, and then, you've got this orthonormal basis here. Hard to picture it, but, and the same change of variable as before works, but now, and also, you want to get it in the right order here. So, okay, so I get it in, yeah, so it's going to be U lambda U transpose. it's the same, it's the same change of variable that we were talking about earlier. But now you have this extra property that the inverse is just a transpose. And so sometimes this is called, we say that A is unitarily diagonalizable. So it's a mouthful, but yeah. That's the spectral theorem, and it's extremely useful thing, tons of applications. Oh, I forgot, there's a moreover part. Moreover, the eigenvalues lambda are real. So there's no complex roots of the polynomial in this case. And in particular, for symmetric matrices, we're always going to be able to order them from the smallest and the min to the largest. Again, this is another added feature that makes life a lot easier when you can order the eigenvalues. If they are complex, there's no order in the complex plane, so, well, there are orders in the complex plane, but not, well, is there an order? There's partial orders. All right. Let's check a few things, right? Let's check this last property. How would you check that the lambdas are real? Right. So first of all, even though the matrix A is real, if lambda is complex, then U needs to be complex, right? So you need to kind of go outside of Rn for the eigenvectors and go into Cn. Right. So, well, this is a standard trick in this kind of verifications. What if we multiply by the transpose of U, but because it might be complex, we need to also take the conjugate, right? So let's do that. The lambda still comes out. So, and now this expression here is real. This is actually the norm square of U, right? Because transpose is the sum, j goes from 1 to n, of U bar j, uj, right? It's the dot product of those two vectors. But if these are complex numbers, this is the sum of the absolute value square. Okay, so that's the two norm square of u, whether whether u is in Cn or Rn, the formula for the two norm is the same. All right, so now let's take this. Let's take this and think about it for a second, right? We want to take maybe yeah. So let's look at this left-hand side here. All right, so how would you write that down in coordinates? You would write ij from 1 to n, u bar I, aij, uj. That's the formula for the quadratic form. So but what happens if I take the conjugate of this expression? Right, the conjugate of a sum is the sum of the conjugates, and the conjugate of a product is the product of the conjugate. So that means that the conjugate of this, right, if I put a bar on top of it, you get U transpose. A is a real matrix, U bar, right? So it cancels this conjugate sign. It doesn't affect A and puts a conjugate over there. Right, so if we take the conjugate here of both sides, we get that U bar transpose AU minus U transpose AU bar is going to be equal to lambda U bar transpose U minus lambda bar U bar. It's not, we don't have to take the conjugate of this because this is a positive number, the non-negative number. So conjugate of a real number is the number itself. And but the thing is that if you write this out, you know, write this out, it may not seem like that immediately, but it's actually the same as this expression. So I guess my question is, do you see how to go from one to the next? Anyone? How do I show that this quadratic form here, U conjugate TAU, is the same as UTAU conjugate? right? I can use this is just a multiplication, so I can move them around however I want them, like that, right? And then I haven't used the fact that A is a symmetric matrix yet, but I can switch the I and the J. And then, because these are dummy variables, I can switch the dummy variables. And call this. So these two things are the same. When I subtract, I get 0. And on this side, I can factor. And so that should be 0. But U is an eigenvector, so it's non-zero. So that implies that lambda. All right, so was that too complicated, or let me know what you think of this.
No, I think that lays it out just fine. It's always more complicated when the details aren't laid out and you have to fill in the gaps. So no, that's good. Thank you.
All right. Yeah. So because of the symmetry of A, you get this kind of symmetry in the in the quadratic form, and that implies the symmetry for the lambdas. And I ran out of time because we only have a minute left. So I think on Friday, I will go ahead and prove the spectral theorem, just for fun, just to refresh your memory. If you've seen it already, it's okay. But let's just go ahead and prove the spectral theorem, since it's such an important thing, which will be at the basis of a lot of our intuition. It will allow us to draw pictures that make sense, and all of these things, right? You need pictures to advance. And so I think, yeah, it's going to be a good little refresher. All right. Any questions? If not, I'll see you on Friday.
Thanks, sir.
See you then.
All right.